Welcome to the 2021 Virtual Materials Research Society Spring Meeting. We are going to have a full week of live symposium sessions, keynote and award talks, a dynamic and exciting virtual exhibit, and much more. This is MRS TV. Welcome to the fourth episode of MRS TV. Today we are joined by MRS Innovation in Materials Characterization Award winner, John Mao. Dr. Mao is recognized for his pioneering research in coherent diffractive imaging and atomic electron tomography for determining atomic positions without assuming crystallinity. But first, let's check out some of the important meeting events from today. Welcome back for another full day of technical sessions, along with a number of keynote talks and special events. Today is highlighted by the plenary address by A. Paul Alivisados, which you can add to your schedule from the special events menu. We also encourage you to visit the exhibit today. The virtual exhibit is available throughout the meeting, but today you will find times when the exhibitors will be staffing their booths for live one-on-one discussions. We will also have a couple of professional development sessions today featuring Elena Levine. These sessions will cover how to network to find virtual collaborators, as well as a facilitated networking snack chat where all of your networking questions will be answered. Find these sessions in the special events menu under professional development. And now we welcome MRS Innovation in Materials Characterization Award winner, Dr. John Mao. Dr. Mao, thanks for joining us.
Thank you, Audrey. Thank you.
Your award citation reads, for pioneering coherent diffractive imaging for a wide range of material systems and atomic electron tomography for determining atomic positions without assuming crystallinity. Can you tell us a little bit about your work and how you came to work in this particular field?
Yeah, this is a very good question. So the coherent diffractive imaging, also termed CDI, which replaces the lens of a microscope with a computation algorithm, has transformed the diffraction imaging and the microscopy field. I started this field when I was a graduate student. At that time, almost nobody believed that a CDI would work. In 1999, we published the first experimental paper on CDI in Nature. Now let me turn to the Atomic Electron Tomography Project, also known as AET. In 2010, I realized that some of the computation algorithms developed in CDI could be used to dramatically improve the tomography reconstructions. In 2012, we published the first AET results, which achieved 2.4 angstrom resolution without assuming crystallinity.
And in your award talk, you discussed two methods that go beyond crystallography. Tell us about those methods and what do they mean in terms of creating new and improved materials?
Many samples in material science, physics, chemistry, nanoscience, geology, and biology are non-crystalline. And thus, their 3D structures not accessible by traditional crystallography. CDI and AET are two powerful methods that can go beyond crystallography. So they will help us gain a fundamental understanding of non-crystalline materials from the nano to the atomic scale. Our experiment showed that textbook theory is incorrect, which means to understand nucleation at atomic scale, we need a theory beyond classical nuclear theory.
More recently, you've led a team that has determined the 3D atomic structure of amorphous materials. Can you tell us about that work and what are some of the applications that could result?
So this is a really very exciting paper, and we just published this week in Nature. With our techniques, now we can peer into these truly atomic resolution structures, and it will help us to maybe better design these materials. Yeah.
And where do you see your research headed in the future?
Yeah, the application is very broad. As I mentioned to you, CDI has really, it's a new way of the new type of microscopy. It's not only just in material science, to the biology community, to the physical science and the chemistry, there's broader applications. And also AET. AET is able to determine the 3D atomic structure of non-crystalline materials. And right now we are trying to push the techniques for low-Z elements or radiation-sensitive materials.
Dr. Mao, again, congratulations and thank you for joining us today.
You're very welcome, Audrey. I really, it's a very pleasure to talk to you.
MRS TV is brought to you virtually from the 2021 MRS Spring Meeting. You can find us on the meeting homepage via the Hub on the navigation menu and through the sessions during regularly scheduled breaks in the technical sessions. You'll also find us on MRS Meeting Scene blog, and by hitting the playlist button, you can check out extended versions of all of our content from award winners to research center visits. It's all on MRS TV. Synthetic biology is changing the way we approach challenges in material science. At the U.S. Army's Combat Capabilities Development Command Chemical Biological Center, researchers are utilizing fundamental biotechnological discoveries to develop the advanced technologies of tomorrow.
We are at the cusp of a fourth industrial revolution, this bio-revolution, and the Department of Defense is eager to harness the value proposition that's being offered here.
Synthetic biology is something that for years has been around and been being developed especially for making new chemicals, but we're really just at the forefront of learning what we can really do to make new materials for a variety of different applications.
We've heightened biotechnology and material science to one of our top priority research areas so that we have the people and the apparatus to be able to really harness the value of biotechnology over the next several years for the benefit of the warfighter.
The U.S. Army's Chemical Biological Center is the premier lab in the world for combating chemical and biological threats. We really have the ability at the Chem Bio Center to span early fundamental research all the way through applied research and testing fielded materials, which is something that you just don't find anywhere else. BEAM stands for Biological Engineering for Applied Materials Solutions. Its main goal was really focused around how to use synthetic biology and biological engineering for making new and novel materials. When we started the BEAMS program, we had great material scientists, we had great biologists, we had great chemists, we had great engineers. But getting them all speaking the same language was something that was incredibly difficult. One thing that we did was we had a lecture series where we had our internal subject matter experts teach each other.
We brought experts on various aspects of material science and biology to share some of their knowledge. We also did a team-based activity where we got the scientists together to work in the lab and work on a hands-on problem.
There are a lot of people at the center with a lot of really diverse skills. Once you just sort of put the idea out there and allowed some people to interact with you, amazing stuff can really start to happen.
The Synthetic Biology for Military Environments program brought together Army, Air Force, and Navy scientists. We worked together on synthetic biology problems. Cell-free systems are an important synthetic biology platform. We're able to use all of the active components you find inside cells activated outside of the context of a membrane-bound organism.
With a lot of modern materials techniques, we've come up with ways of taking reactions that previously had to happen in a container in a laboratory and literally have them laid down on a simple piece of paper. We have some paper-based sensors that are effective against chemical warfare agents like sarin or VX, for biological hazards too, things like anthrax and ricin. The end result on the sensor is essentially the same, and it is a little spot that starts off one color and changes to a completely different color to indicate that that threat is present.
At the Chem Bio Center, not only do we make a lot of things in-house, but we work with a lot of external collaborators at universities as well as within industry. So what this allows us to do is take early fundamental research and then work with industrial partners to make them into real products that we can put into warfighters' hands.
The VOC-Kit is a little portable reader. We'd made these little tickets that had about 80 different spots of dye on it. This is way too complicated for somebody to read by eye, so we knew we needed a machine to read them. We probably worked with 3 different companies. One was the company that was working with the arrays for us, and one of them was making injection molds for us, and another one was integrating circuit boards for us.
One of the collaborators that we work with is the Massachusetts Institute of Technology. They have a very unique way for making novel carbon materials. We can incorporate in oxygen, nitrogen, sulfur groups in very specific spots and have them be able to interact with chemical threats in a way that we've developed. Within the Chem Bio Center, not only do we have the ability to synthesize and make new materials, we have the ability to uniquely characterize these materials.
We use a number of different techniques for studying the chemical interactions on these new materials that we're developing. On an ultra-high vacuum chamber, we introduce that surface to chemical agent, chemical contaminants, pollutants that might be in the atmosphere, and we can use our IR spectroscopy at the same time as our mass spectrometry, and then we can see how the surface has changed using something like XPS. With the new chambers that we have, we can go all the way up to atmospheric pressure. This is really advantageous for the BEAMS program because some of these studies involve biological samples.
Prototyping, getting things into the hands of the warfighter and letting them break it is critical. That requires not milligrams of material, but kilograms of material. Here at Aberdeen Proving Grounds, we have the only pilot-scale biomanufacturing facility that exists within the Department of Defense. Over the next several years, we're going to conduct a multi-phase upgrade of that facility. We're going to first increase the capacity. We're at 1,500 liter fermentations now. We're going to move up to 5,000 liters. Advanced materials has become central to the way we are choosing and selecting and prioritizing what we manufacture in the facility.
At the Chem Biocenter, you have a real opportunity to grow a career here. The projects that we work on are very riveting and things that we can see go from fundamental science right into real-world products.
The center values generalists because our mission changes as the need of the warfighter changes, so we're encouraged to continue to develop throughout our careers, take on new skills and try new challenges.
Getting to work with this high-end equipment and apply it to a real-world problem, and also a problem where we're talking about how to protect our soldiers, it really gives a lot of meaning to what you do when you come to work every day.
That's all for the 4th episode of MRS TV. Join us tomorrow as we host MRS Postdoctoral Award winners as they discuss their groundbreaking research in self-healing materials and ferroelectric polymers.